So now we develop circuitry for binary multiplication. Um, so before we go to design of multi-bit binary multiplier, let's first see how a one-bit binary multiplication works. Suppose we have these two inputs, A and B, and we have this output product. So because since we have two inputs here, so we would have total number of four input combinations where we could either multiply a zero with a zero, and that in that case result will be zero, and we could next multiply a zero with one, and in that case product will be again zero, and we could multiply a 1 with a 0 and still the product will be 0, while in case of uh, both inputs being 1 we will have a product that is 1. So in this case the product or multiplication between two binary bits um, results in this expression that involves an AND gate between the both inputs, right? So now, so we can multiply two bits using by uh, connecting them in an AND gate. So now once we have this expression for one bit multiplication, let's move ahead and multiply and develop a two-bit multiplier. So in order to develop it or in order to design a two-bit multiplier, let's look at the multiplication of two binary bits. Suppose we have this two-bit number b, b0 and b1, and another two-bit number a0 and a1. So when we multiply these two numbers, we actually multiply each this bit a1 with each of the bits in the b, and then we multiply this bit b a1 with each of the bits in the b, right? So let's kick start the process. So let's multiply a naught with b naught, and by multiplying we mean we AND a naught with b naught, because in the previous part of this lecture we saw that multiplication of two bits is nothing but the AND gate, right? So and then we multiply a naught with b1, and in that case we have this AND gate a naught into b1. So, and then in multiplication by definition uh, we leave this spot empty, and then we multiply this a1 with b naught. So here we have this AND gate a1 into b naught, and then we multiply this a1 with b1, and here we have this AND gate a1 into b1, right? So as a result of this, we have here we have a naught b naught as the first bit of the product, or right, or the least significant LSB of the product, and here we have a naught b1 plus a1 b naught as the second least significant bit, um, or the second bit of the product, right? And here, since this addition can generate a carry, um, so we can have a carry here. So in that case, we might have an adder here, but this would be, if not, this would be the final bit of the product, right? So, and let's say add carry from previous half addition. And so since this particular addition has only two inputs, so it means it's a half addition. And again, this would, if there is a carry, this would also be a half addition, right? So in order to make a circuit for it, first let's implement this thing. This, so this is an AND gate, and the result of this AND gate is goes directly to the product as its first bit or least significant bit, right? And and then we implement this thing since we need a half adder here. So let's just we have this half adder that adds two inputs, where this is the AND gate, right? So, and as a result of this addition, we get the second bit of the product, and the carry goes to the next half adder that adds this carry with the result of this AND gate, right? So, and this gives us the third output. Okay, so so this is a more clean and neat drawing of the 2-bit binary multiplier. So now we move to the design of a 4 by 3 bit multiplier, where one input is. So this is how multiplication of a 4 by 3 bit binary numbers unfolds. Which is straightforward actually. You multiply a naught with each bit in in B, which results in these AND gates, and then you multiply each bit, the bit A1 with each bit in B, and in that case you get these AND gates, which are of course shifted by 1, which is an inherent property of the multiplication, and then finally you multiply the bit A2 with each bit in the B, and that gets you to these AND gates, and again you shift these AND gates, the resulting bits, by two times to so end up with this these bits and the multiplication, uh, which are bits of I mean the bits of your product, right? Rather part of your product, right? Okay, so now the task is here is to how to make a circuit that could implement this whole process, right? So this A naught B naught is an AND gate that is directly going to the output. So let's draw this A naught and B naught, right? So this is directly going to the output, say P naught. P naught is the product, right? Maybe let's put the C naught because this is the convention that your book has used. Now just look at this addition. If we add a 0 here, it looks like addition of two 4-bit numbers. And so in order to perform this, we can use a 4-bit binary adder that we already know how to develop. Uh, so uh, so uh, so let's put a 4-bit binary adder here. Uh, right. So and in this adder we have 3 AND gates here. And here we have B3, B2, and B1, and the fourth or the most significant input or the most significant bit here is 0, right? And then the other 4-bit number has again 4 AND gates. Uh, Maybe it's not that pretty, but I will show you a clean diagram later. So this is, say, A1, and each of these AND gates have input from the number B, B3, B2, B1, and B naught, right? So this, so result of this, we will have 4 sums, say S1, the 4 bits in the sum, right? S2, S3, and S4. So this is S1, the sum of this, and it will directly go to the output. So this S1 will be directly part of the product, like the second bit of the product, right? While the S2, in this case, this is S2, it will be added to the, let's just change the color for clarity. This is S1, and it will go directly to the product into the answer, and this will be S2, and we will add this into A2 plus B naught to get to the product, to get the third bit of the product, right? And here we this is S3, and we will add this into A2 plus B1 to get the fourth bit of the product. And here we will have S4, which is given here. So here we will add this into A2 plus B2 and to get this fifth bit in the product. And the final bit so will be obtained by adding A3 B3 with the carry. So let's say see we have a carry C carry. So now again, as you can see, we have another 4-bit. We have an addition that involves two 4-bit binary numbers. So we will again use So two 4-bit binary, another 4-bit binary adder. So here we the one of its input would be S2, the other would be S3, and the S4, and then the carry, that will also be one of its input, the fourth input of the first 4-bit number, as you can see here. So, and then on this side you will have 4 inputs that will have 4 AND gates. So here you have this is uh, and here you have B3, B2, and B1. So as a result, you will get 4 bits in the sum, and this will be then C1, C2, C3, C4, and 1 bit will come from the carry, and that will be C5. So you will have I think I've made this mistake here. I think this is C1, so this should be C2, C3, C4, C5, and C6. So a multiplication of 4 bit number with a 3-bit number will result in a 7-bit result, product rather. So excuse me for the ugliness of this circuit. This circuit, I guess we can draw a lot better than this. So in the next slide, I show you a much more clean and neat circuit that performs exactly the same thing. So as you can see, this is how we can design a 4-bit binary multiplier. So this is the end of this lecture 5.